Okay, does someone want to take us through how they solved this one? Zainab, go ahead. Okay, gentleman in the front. Be quiet. Sorry. Go again. Just wait till everyone's ready here. Okay. So you lawned both sides. And then what did you do?
X plus 3 is whatever the log E.
Okay, so parachute that guy down.
And since log E is equal to 1, I just cross that out. And then log E minus E, get negative 1.391.
Perfect. So I think we can actually probably just leave this in exact value. We'll just leave it as the ln of 5 subtract 3. This is not the ln of 2. Okay? This is the ln of 5 and then subtract 3, right? So I don't want to do 5 minus 3 because the 5 is inside the ln. If it helps you to do brackets around this or something like that so you remember that the 5 is part of the ln, then just make sure you do that. We definitely don't want to simplify that to ln of 2. Good, any questions on this one? Okay, we are going to do a proof, which I think will help you with that the first question on page 250 something, 256. And it is the proof of any base b to the exponent x. So you might actually need kind of this whole right side of the paper here. So if you want, you can just draw a line down there and use that whole right side for your proof. So b is going to be any number. Okay, so we recognize as we're proving this that the b is actually, because it's a variable, it's a changing value. It could be 2 to the x, it could be 3 to the x, it could be a fraction, whatever. So this kind of affects how we explore the derivative of this a little bit because we'll have to look at it for various bases because those are all different exponential functions. But the hope is that we can kind of see a pattern in what's happening as we change the base. Okay, so in order to prove, of course, we're going to use Newton quotient as usual. So in order to use Newton quotient, I want to think about b to the exponent x as if it's the function f at x. And then we know for Newton's quotient, we also need f at x plus h. So we like to do that maybe just ahead of time so we know what we're plugging into the function. So this is just telling me that it is going to be b to the exponent x plus h when I sub into the Newton quotient there. Okay, so as we use Newton quotient, this is going to help us find the derivative. So it's the limit as, h approaches 0. Of f at x plus h minus f at x all over h. Okay, so we're going to sub in what we know. F at x plus h is b to the exponent x plus h. F at x is b to the x. And then we have that over h. Okay, we're going to use some exponent rules here to help us with this a bit. My exponent rules tell me that if I ended up adding exponents, that came from multiplying two bases with exponents. So another way that I can write b to the exponent x plus h is b to the x times b to the h. Okay, because exponent rules tell us that when I'm multiplying two values with the same base, I keep the base and I add their exponents. So we're kind of working in reverse than what we're used to since grade 9. So we'll notice here that there is now a common factor between these two terms that I can actually factor out, which is b to the exponent x. So we're going to take that out. And what remains is b to the exponent h minus 1 all over h. Okay, so still not super helpful because if I try to sub in at this point, I still have, I'm going to get 1 minus 1 here, so I'll get the whole top as 0, and then I'm going to get 0 over 0, which is still indeterminate form, which is a problem for us. We did talk about in our proofs of some of the trig functions that if I'm looking for where the limit as h approaches 0 and part of my function doesn't have an h in it, I can actually take that part of the function as long as it's like a multiple, and I can write it out front as a multiple here because that part of the derivative will not be affected when I'm taking the limit, or I should say the limit, as I'm taking the limit of something with only x in it. So what I can actually do is I can take this part and I can write it out front as a multiple of the limit of what remains that has to do with h's. So we're going to take the b to the x out. And this is what I'm interested in now, the limit as h approaches 0 of this guy over on the right here, b to the exponent h minus 1 all over h. Okay? So because b is changing, this can be a difficult thing to pinpoint, right? Because b could be anything. It could be 2, it could be 3, could be 4, could be 5, and so on. So that's kind of a problem for us because I can't actually just like put this function in and see what it's approaching. It changes all the time with the function as the b value changes. So I want to call this guy right here, for now, I want to call this section of our function, this is going to be k. All right, so I know right now that when I take the derivative of some function b to the x, that the derivative dy over dx is going to give me back that base to the exponent x times some value k. And I'm interested in what that value k is. K is going to be some kind of value. So we're going to use kind of like a chart to observe this. And we're also going to use Desmos to look at this function with a variety of bases of b. Okay, so we're going to use Desmos for this. If I were doing this by hand, we're using it now just so we can observe and see. If I were doing it by hand, I can try various bases of b and choose h values that are getting really close to 0. Maybe I choose like 0.00001 with a variety of bases of b. But because we have access to graphing software right now, we might as well use it. So we're going to pull this up on Desmos. And instead of h, I'm going to use x here, but we know that it's our h value. So I want b to, no, not b to the x. I'll start with 2 to the x minus 1 all over x. This is our first function. Let's go into projector mode here. Yes. Okay. So we are looking where this guy approaches 0. Before we start our observations here, we're just going to set up a little chart to see what's going on. Okay, these will be the variety of functions that we're observing. I'm going to observe maybe like 2, 3, 4, 5, just as an initial observation of how the base can change and how the derivative changes with that. Okay, and then I want to know what that guy up there that we labeled as k, I want to know what that is approaching as h approaches 0 for these variety of bases. So I'm interested in my k value, which we know to be the limit as h approaches 0 of this equation. as we use a variety of different bases. So of course the b here is going to be equal to the b here, and I'll switch this as we go through Desmos and look at what h is approaching 0 there. And then my final thing over here will be my final derivative. We know that the derivative of y equals b to the x is going to be equal to our k value times b to the x. So what we're most interested in here is this center column. That's what we're using Desmos to observe right now. Zainab?
How do we know that e to the h minus 1 over h is k?
We let it be k just for our purposes right now. It's some value. We don't know what that is just yet. Okay, so first one, I have it graphed. I am interested in the value that we are approaching as we get towards 0 here, or the y-intercept. Okay, which should, it is undefined right on here. But if I get closer and closer and closer to this, hopefully we can get a more accurate value. Of course, when I get right on it, it's undefined, but it looks like it's going toward like 0.686, if you guys can see that. The more precise value of this, we can just call it maybe like 0.69. I think that's pretty close. So 0.69 is what we are approaching for this function when b is 2. Okay, now I'm going to sub in 3 here, and we're going to look at what that approaches as we go towards 0. Okay, and you'll notice that it's changing because they're different functions. So as we get towards 0 here, it's like 1.105-ish, 1.087 is that one. That's a pretty good one. I'm going to tell you the more precise value, which is, this is approaching 1.0986. Okay, again, we can also calculate this by hand, and actually with our graphing here, it's probably more accurate to calculate it by hand and sub in something for h as we change b, like 0.00001, just because it's hard to get that close on the graph. So I'm just giving you the more precise values that could be calculated by hand. Okay, now let's change it to 4. Okay, we're going to look at what is being approached as we approach 0 here. Okay, this is actually really close right here. 1.382, something like that. The more precise value is 1.386. Okay, and then if I change this last one to 5 and we approach 0 on that guy.
1.609.
You got it.
6094.
Okay, so 1.609 as we look at this. How did you figure that out?
I found the derivative at 0.
The derivative at 0. What do you mean? Did you plug in like 0.0001 or something like that?
No, I calculated dy over dx at x equals 0. For y equals 5 dx.
Okay. So how do I, if my k is always changing, how do I say what k is? That's a problem, right? Because if it's always changing, I can't say k is 2 or k is 3 or whatever, right? Mark? Well, it's increasing just because our base is increasing, right? So we need a more general statement to tell me, like, what is the derivative of this? I'm never going to say in a derivative it's infinity or anything like that, right? So guys, tell me what happens when you calculate ln of 2. Oh, okay, so what's ln of 3?
1.09.
Okay, and yes, the pattern continues. The ln of 4 is equal to this value. And the ln of 5 is equal to this. So as my base changes, that k multiple is the ln of that base value. So the derivative of y equals 2 to the x is the ln of 2 times 2 to the x. And then the derivative of y equals 3 to the x is the ln of 3 times 3 to the x, and then so on, right? So the derivative of 4 to the x is the ln of 4 times, not 3, 4 to the x, and so on. Okay, so I think we can create a more general statement for this. Oh, and I put 4 again. So can somebody create a statement for us which tells us the general value of k if I have a base of b to the exponent x? Zainab? Ln of b. Perfect. So, so here our k value is equal to the ln of b, the base. Devin?
I don't understand why k is ln 2.
So we just observed from the graph that this part of our function, the limit, is approaching these specific values. And I was just showing everybody that these values are actually like this is the ln of 2, this is the ln of 3, this is the ln of 4 and 5, and so on. So we observe that from the graph. So this k value, this is what we were observing, right? The k value that I'm talking about here is this limit. So we were observing those values that were being approached, and they happen to be the ln of the base every time. Okay, so yeah, sir.
So, like on the rightmost column, like right above it says like derivative of y equals b to the power of x.
Yep.
Like, I'm just confused on like what that rule is. Like,
So we're proving the derivative, right, of b to the x. So this Newton quotient thing that I just came up with here, this is dy over dx of b to the x.
oh right.
Yeah. So we're just using this chart to kind of like accumulate all of that information. Okay, so the derivative of any, you might want to write this down and like box it, of any base to some exponent x, so of our y equals b to the exponent x, is dy over dx is equal to the ln of the base times, you get that base and the exponent back. So this is our derivative. Okay, that is a derivative rule. So highlight it around there, put some stars, whatever you want to do.
Are you going to ask this on a test?
I will ask you on a test to prove either something to do with E ln, there'll be other proofs in this second half of the unit as well, or a trig proof.
So it could be this?
Could be. Okay, so because I've already proved this, I can actually use this to prove the derivative of e to the x. So because my derivative is for an exponential function, I can always also use this for my special exponential function e to the x. So this is just a really quick proof that if I've proven this, I can use, and it's snowing, cool. I know, it's so sad.
It's so
I know. I shouldn't have said that. Now we're off to ask.
What do you mean? It's almost April and it's snowing. It's global warming.
Global warming.
Fridays for the future.
Okay. Let's refocus. I regret my decision. So can somebody tell me what my derivative of y equals e to the exponent x is?
ln x.
Ln of e, ln of the base, right? Times what? Okay, and what is ln e? Okay, so this is actually a pretty cool function because the derivative of e to the x is itself. I know. Okay, so we are allowed to prove it this way because we've just taken the time to prove this up here, but there also is a separate proof for the derivative of e to the x if you wanted to just prove this alone. I'll give you the link here, but because we've already gone through the whole proof of this, I don't think that that's necessary that we reprove this whole thing. So the derivative of e to the x is e to the x. Of course, if I change things within that exponent, I need to make sure I do chain rule properly, so just be mindful of that.
Can we do an example of that?
Yeah. Okay, so we're going to practice some derivatives now. I know. So we are differentiating with respect to x here. I am going to change my notation to dy over dx. What is the derivative of 3 to the x? We get back itself and then multiply it by? Okay, great. So it's the ln of 3 times 3 to the x. Derivative of 1 is 0. So this is the answer. Okay. Derivative of 4 to the x. Good. Good. And derivative of negative 5? 0. So we get this. Beauty. Okay. Derivative of any constant is 0. So, right, Aiden?
Yeah.
All right. We're going to find the equation of the tangent line. That is tangent to the curve y equals 2 times e to the x at the x value ln 3. Okay, so I need to find the derivative to start. This is kind of like the constant multiple rule. So if I have a constant multiple out front, that's just going to kind of hang out front. And then I will do the derivative of the second part. What is the derivative of e to the x? Ooh, e to the x. Lovely. So that's our derivative. It ends up being the same. Yep.
The one, what is in front of the, like, what are the two, you know, kind of just write it.
So assume that I did product rule here, right? And I considered this my first and this my second. The derivative of the first is 0 times the second plus the first times the derivative of the second, which is e to the x. So the reason why we don't really need to do that is because this term will always cancel when I have a constant multiple. Okay, so I'm finding the equation of the tangent line. So I need the slope to start, where x equals ln 3. So I'm going to evaluate the derivative dy over dx at an x value of ln 3. This is usually the notation that we write if we have this type of dy over dx notation. Mark?
Wait, why does it say dy over dx is equal to?
This is the derivative of the function. Because the derivative of e to the x is e to the x.
Oh, yeah.
Okay? So we're going to evaluate this at ln 3. We just discussed this. What do I know about this part of the function? What is that equal to? 3. Okay? So the little tip here that we talked about in our homework take up is that e to any ln of a value, let's call it a, is equal to a. Okay, you can also calculate it on your calculator. It says tip. Sorry. I know it looks kind of weird. I shouldn't have written it like this. Let's just do that. We'll just do that. I can also calculate it on my calculator. If I calculate e to the exponent ln 3 on my calculator, I will get back 3. So this will be 2 times 3, which gives us 6.
E to the exponent ln e.
Ln a
Oh, sorry. Yeah. So okay.
equals that a value, whatever it is.
Like always? Like
Always, yep. Okay, there's my slope of my tangent. So far I know this. I need to find my b value. Now the interesting thing about this is that I actually don't have to calculate the y coordinate for the point on the original function y equals 2 to the x because I already calculated the value at ln 3 and the derivative and the function are the same. So my point on the line is actually the x value is ln 3 and the y value is 6. Because when I sub in ln 3 here, I'm going to get 6. So that's a point on the tangent. This only happens because my derivative is the same as my original function. Otherwise, I would be plugging this x coordinate into the original function to find the y. But we already did that here in the derivative. Olivia? Yeah, sure. Yeah. So this 6 comes from the original function. This 6 comes from the derivative, and it's the slope of the tangent. So the slope of the tangent just so happens to be the same as the y coordinate of the point on the line because the derivative and the original function are the same. Okay, so I want to find my b value, so I'm going to plug in my x and y here. And so my b is equal to 6 minus 6 times ln 3. And then I'll just sub it back in to the equation here. Okay, and then if we want, we can common factor a 6. It doesn't really matter. Okay, so if you want, you can express it like this. Okay, I think either of these two answers here are fine. Okay, we've got one question left. I think we can finish it up. Do you guys feel like you need a break, or do you want to just finish? Just finish? Okay. Are we good with this? Any questions on this guy? Okay. Last question.
Classic question.
Are we ready, people?
Wait, biology? No. You're 3. Let me know.
Okay, are we ready? Okay. Aiden just said, classic question. This is a great question. Biologists is studying the increase of population in a particular insect in a provincial park, or of a particular insect. The population triples every week. So this is something we've been studying since like grade 11, right? Since we were introduced to exponential functions, how population growth works. So this population triples every week. We're going to assume the population continues to increase at this rate. And initially, there are 100 insects. Determine the number of insects present after 4 weeks. No derivative needed with this. All we need to do is set up the equation, and then we're going to evaluate it at 4 weeks. So just as a reminder, this is kind of our general equation that we work with. This is from advanced functions. Maybe we'll work with some value b, and then it will be t over some other variable. We can call it n or whatever. And n is going to be kind of like our growth or decay period. So Okay, this is our initial, and this is our future. And t is total time. Okay, so what do we know about this scenario? What can you guys fill in for me here? Zainab? Good. Initial population is 100. Growth or decay rate here? Triples, yep, 3. Do we have the growth period? 1 week. So it'll be like t over 1, which we know is just t. Okay, so for part A, I think this is pretty straightforward. All we want to do is just evaluate A at 4, so when time is 4 weeks. I also just want to be mindful about making sure that if I'm calculating 4 weeks, that my growth period is in weeks as well. So units of measurement with time are important here. So we'll have 100 times 3 to the exponent 4. What does that give us? 8,100? Pardon? Yeah, you could, but it's going to be challenging for you when you go to part B if you don't have an equation. So, okay, we're almost there, guys. Stay with me. So, how fast is the number of insects increasing when they are initially discovered and at the end of the 4 weeks? So we want the rate of change in population. And when I think rate of change, I want to think derivative. That is what the whole idea of calculus is based around, or at least the calculus that we're studying is find instantaneous rate of change at a certain point. So I need to find the first derivative of this function, which requires me to use some of the knowledge that we learned today. So constant multiple rule, that 100 is just going to kind of hang out here. What is the derivative of 3 to the exponent t? Ln 3. And then we get that base and exponent back, 3 to the t. Okay, now my job is just to find out rate of change in population of insects. Sorry, I can't go any further up on this. For part I, we'll do it just like up here. For part I, I'm interested in when t is, what's initial time? 0. So I'm interested in A prime at 0. Which will be 100 times ln 3. So I'll have you guys calculate that for us.
109.86.
Oops. That 0.00089 of that insect is very important. What did you say, sorry, 109?
9.861.
Okay, so can we say approximately 110 insects? No? Okay. Okay, and then second part, yep, Mark?
Like, wouldn't you round down because you can't have a fraction of an insect?
Yeah. You.
Tell us that the 0.00001 of an insect.
It's very important. We're just getting an approximation. If you say 109 because you can't have 0.86 of an insect, I'm fine with that. Okay? Last one, we want to do 4 weeks. So you are evaluating A at 4, or A prime at 4, I should say. Sorry, again, I can't go any further up so that you can see. So,
It's exactly equal to 65, 61.
yeah? I don't need my squiggly equals.
Oh, wait, my brain's broke.
Yo, is it 65, 61?
It is.
Oh, I did something wrong. In my final answer, that's okay. In my final answer, yes. I did not put my proper rate of change here. Insects per week, because it's a rate of change.
Sorry. It's 88.
Yeah, that's what
Oh, is it wrong?
Oh, no.
How could you? Devin wrote in pen.
You've done.
Okay, so what's the correct answer?
Sorry.
There is no sorry.
88, 98? Do I need a squiggly equals?
No.
No? It's exactly equal to 88, 98?
It's, it should be 88.99.
No, it should not be. You don't have 0.76 of the insect.
That's 0.7595.
Okay, great. So 88, 98 insects per week. Yes, that's what I got as well.
That's a whole other.
Okay, I will pause here or stop.